Okay, section 14.8, standing waves. Imagine setting up a device like the one shown in the figure. A stretched string is connected to the vibrating blade and at the other end to a wall. Traveling waves then reflect from the ends and move in both directions of the string. The incident and the reflected waves combine according to the superposition principle. If the string vibrates at exactly the right frequency, the wave appears to stand still, which is why we call it a standing wave. A node occurs where the two traveling waves always have the same magnitude of displacement but the opposite sign, so the net displacement is zero at that point. There is no motion in the string at the nodes, but midway between two adjacent nodes at an antinode, the string vibrates with the largest amplitude. The figure shows a snapshot of the oscillation of a standing wave during half a cycle. The red arrows indicate the direction of motion with different parts of the string. Notice that all points on the string oscillate together vertically with the same frequency, but different points have different amplitudes of motion. The points of attachment to the wall and all other stationary points on the string are called nodes. From the figure, we can see that the distance between adjacent nodes is 1/2 the wavelength of the wave. Let's look at the figure where a string of length L is fixed at both ends. First, the ends of the string must be nodes because these points are fixed. Let's imagine we displace the string at its midpoint and release it. The result is the vibration shown in the lower figure. In this case, the center of the string is an antinode labeled A. Note that from end to end the pattern is NAN, that is node, antinode, node. The distance from a node to its adjacent antinode, N to A, is always equal to a quarter wavelength. In the case here, there are two segments, NA and AN, so let's calculate the wavelength. Next, let's write the equation for the speed of a wave on a string, where F is the tension in the string and mu is its mass per unit length. Substituting, we get this relationship, which is the lowest frequency of vibration and is called the fundamental frequency of the vibrating string, or the first harmonic. The first harmonic has nodes only at the ends, the points of attachment, with node-antinode pattern of node-antinode-node. We can construct this next harmonic, called the second harmonic, also called the first overtone, by inserting an additional node-antinode segment between the endpoints, as shown in the figure. This makes the pattern NANAN, or node-antinode, node-antinode, node. Let's count the node-antinode pairs, NA, AN, NA, and AN, for 4 segments in all, each representing a quarter wavelength. So we can calculate the wavelength of the second harmonic and use our result to find the frequency. The frequency is equal to twice the fundamental frequency. We can construct the third harmonic, or the second overtone, in a similar way, inserting one more NA segment. We get the pattern of nodes NA-NA-NA-N. There are 6 node-antinode segments, so let's calculate the wavelength and frequency. All the higher harmonics, it turns out, are positive integer multiples of the fundamental. The frequencies F1, 2F1, 3F1, and so on form a harmonic series. This is a multi-flash photograph of a standing wave on a string. When a stretched string is distorted, to a shape that corresponds to any one of its harmonics. After being released, it vibrates only at the frequency of that harmonic. If the string is struck or bowed, the resulting vibration includes different amounts of various harmonics, including the fundamental frequency. Waves which aren't in the harmonic series damp out. Basically, when disturbed, the string selects the standing wave frequencies. The presence of several harmonics on a string gives stringed instruments their characteristic sound, which enables us to distinguish one from another even when they are producing identical fundamental frequencies. The frequency of a string on a musical instrument can be changed by varying either the tension or the length. The tension in guitar and violin strings is varied by turning pegs on the neck of the instrument. As the tension is increased, the frequency of the harmonic series increases. Once the instrument is tuned, the musician varies the frequency by pressing the strings against the neck at a variety of positions, which changes the effective lengths of the vibrating portions of the strings. As the length is reduced, the frequency again increases. If the mass per unit length is increased, a string of fixed length can be made to vibrate at a lower fundamental frequency. Next section will be forced vibrations.